Hey everybody. So, welcome to our pre-video. We're going to talk about how counting things leads you to the ability to measure performance in machine learning. We've already talked about the existence of this confusion matrix. We've shown it a couple of times in our scikit-learn notebooks. How do we interpret this? Well, we have some true label because we have supervised machine learning here, right? We know the proper labels for each one of our training data points. So because of that, we can break up our data set into a table where we list, okay, on this row, only those things that are actually positive class. And on this row, only things that are negative class. Now, we also have columns in the confusion matrix, and that goes with what our machine learning system predicts. So over here, we count up in this column only the things that we predicted as positive class. And in this column, only those things that we predicted as negative class. So good performance lies on the diagonal here, right? These are things that are actually true class, which we have predicted as true class. Those are called true positives. And over here, this is also good because those things are actually negative class and we predicted them as negative class, so they are called true negatives. Now the off diagonal is bad stuff. We don't want these. These are errors. Our machine learning system has made 3 errors here, right? 2 plus 1. So those 3 errors, they come in 2 different types. So over here we have a false negative. This is actually a positive class instance, but we have called it negative class. Now over here we have false positives. So this is actually a negative instance, but we incorrectly called it positive class. To help you with the wording, the false positive and false negative, the positive negative goes with our predictions because we predicted positive and it's a false one. Okay, great. So this is awesome because it shows us how we can understand our errors systematically. So for instance, what if we were doing an application where we never, ever, ever want to miss a single positive class instance? If we never want to accidentally label positive class instances as negative class, we would care greatly about our false negative rate. And maybe we don't care so much if we have false positives. Okay? So you can think of applications like that, like cancer detection. You would never want to have a false negative for a cancer detection because that would mean the person went untreated, right? And it would be relatively less impact if we accidentally called a healthy person, told them that they had cancer. At the very least, they're not going to lose their lives, which was what's going to happen for any false negatives over here. Okay, so the confusion matrix can be generalized. This has been so far for the idea of binary classification. But, we can take any number of categories as long as it's not so many that you can't see the confusion matrix well anymore. And we can generalize that so that, once again, diagonals are good stuff, off diagonals are errors, but we no longer have names for these kinds of errors. So, but you can see that systematically here, it's the chin strap penguins that keep getting confused for other species, right? And so you can still see the systematicity of your errors. So in general, we want to have a high number of true positives. This is called the true positive rate, right? So if you take those numbers back over here, right, and divide them, so take this 46 and divide it by the total number of penguins, that's the total number of Adelie penguins, that's the true positive rate for Adelies. Right? Here, the true positive rate is 10 divided by, 15. So 10 over 25. So that's the true positive rate. No. Dang it, I've said this wrong. Haha. The true positive rate is 10 over 12, right? For all the actual positives, there's 10 positives. There are 12 total actual truly positive data samples. 10 we said were positive, 12 that were actually positive. So that is our true positive rate. It is the probability that we predicted something to be positive given that it's a true label. Okay, so we take the counts in this cell here and divide it by the total number of true labels, which is the entire row. Okay, this true positive rate is also called sensitivity. It's also called recall. Now you can remember those names, sensitivity and recall, because we are sensitive to the true positives and we can easily recall any true positive and show it with our test. Now, the reason it has two names is because different factions of engineering reinvented the wheel and used different terminology. I'm sorry for that. But true positive rate, sensitivity, and recall, they are all exactly the same thing. And unfortunately, you will see different people use different words for this same thing. So the true negative rate is the probability that we predict something is negative given that the true label for it is negative. This is called specificity. You can remember specificity as a name because our test is specific only to actually true positives, truly labeled positives. So it only detects positives, it's specific to positives. So anything that's truly negative, we predict it as negative. It has high specificity. All right, so we want those to be high. And our error types, false positives and false negatives, are going to be similarly able to be talked about as probability of getting a positive label given that the true label is negative, and vice versa for the false negatives. We want those low. Okay, all of this stems from our friend, the Reverend Thomas Bayes, who spent his life counting things and therefore figured out some axioms of probability for us. Let's look back at that cancer example. So if we have a positive test, right? The probability that we get a positive test given that somebody actually has cancer, okay, that is going to be the probability of A, of a positive test, given B, that they actually have cancer. It turns out that you can see just graphically by looking at these Venn diagrams that this probability, the probability of event A happening, given that event B has happened for sure, is just equal to the intersection of the two events, probability of A and probability of B happening simultaneously, divided by the probability that B happened in the first place. Okay? This is Bayes' rule. The joint probability divided by one of the probabilities gives you the probability of A given B. Now, this is a symmetric relationship. I just couched it in probability of A given B, but you can easily do the same thing for probability of B given A. And it turns out that that's going to have the same nature, the probability of the joint divided by the probability of one of the events. And therefore, you can do what's I like to think of as the Bayesian presto changeo, which is that you can couch the probability of A given B in terms of probability of B given A, the flip, the reverse. Okay? So if this is a little confusing to you, you should go back and review Bayes' rule, conditional and joint probabilities from materials that you had from your statistics class, because now we're just going to use it at this point. Maybe my 1 minute on the topic isn't quite enough for you. So let's imagine our cancer test. We have this thing that is going to make a couple of errors, unfortunately. We have a 0.1% chance to have cancer, is what we're going to say, right? We're going to say that when we look at the probability that any one random person on the street, we stop them and we ask, hey, do you have cancer? That a very, very few of those people, 0.1%, are going to have cancer. We don't have to actually do this by asking people. We can use the medical literature, thankfully, to find the probability that a given person is cancerous. So our test makes errors, right? And we're going to say that our test is going to give us a false positive, tell us that somebody is truly healthy. It's going to make a false positive. It's going to tell us that a healthy person is cancerous wrongly predicting them being cancerous 2% of the time. This same test is going to have a false negative rate. That's 10%. Okay? If a person is cancerous, they are going to be told they're not cancerous 10% of the time. And as we mentioned earlier, that's probably a pretty bad test, right? You don't want to be doing that with cancer patients. You want to catch every cancer patient. But for the sake of demonstrating how this works, I'm going to use this bad test. So we can draw up a contingency table. We can draw up a confusion matrix. So let's start with the idea that we have 10,000 people that we are applying our test to. Okay? Now, some of those people are actually healthy, and some of them are actually cancerous. In fact, we know that cancer is rare, only a 0.1% chance. So, I'm so sorry. I thought I killed this animation. All right, whatever. So I just animated it out. But of the 10,000 people, only a 0.1%, that is 10 of those 10,000, are actually cancerous people. The other 99.9% are healthy. Okay, hopefully I don't have that animation stuck in for the rest of these slides. So, and I do. Great. Well, let's apply, I guess I might as well use the animation, huh? So of those healthy people, only a certain fraction of them are going to be predicted as healthy. Actually, let me just kill this animation. So bad. So these healthy people are correctly predicted as healthy. These healthy people have been incorrectly predicted as being cancerous. 2% of our population of our healthies have accidentally been predicted as actually cancerous. Now we also have our false negative rate. Of our 10 actually cancerous individuals, only 9 got told by the test that they are cancerous. 1 person got a false negative result, and their doctor will not be treating them. Bad. Okay, now we can sum up the tables. So if we sum up the 9 and the 200 here, we get 209 total positive tests, and we get 9790 total negative tests. By the way, these things don't strictly add up because there should be some fractional stuff in here that I kind of, just deleted, but it's within 1 out of 10,000, so it's not bad. So this basically adds up to that. This adds up to that. This adds up to that. This adds up to that. Everything should basically add, or it would if I put in our fractions here. Okay, this contingency table, this confusion matrix, is showing us how good our test is. Our machine learning test, if you will. Okay, let's apply Bayes' rule. So given our table, which I am sad to say is still animated, okay, given this table, we can ask, okay, I got a positive test. I'm one of these people in this column. Should I be running around screaming and freaking out that I have cancer? Application of Bayes' rule will show us whether or not we should freak out at this point. So we know from our earlier definition that the probability of cancer, which occurs right here in the Bayes' rule, is pretty low. It's 0.1%. Okay, now let's ask ourselves about the probability of a test being positive given that we are cancerous. So the probability of a test being positive is 9 out of the 10 cancerous patients are going to test positive given their cancer. This is the specificity of the test. Okay, so the probability of the test being positive at all is just the sum of this entire positive test column, 209 total positive testers, out of the 10,000 total. So that is, 0.02. All right, so we can plug those numbers in. And it turns out that when we do that, 0.9 times 0.001 divided by 0.020, the answer falls out to, given that I have tested positive, given that I'm in this column, I have less than a 5% chance of actually being cancerous. In fact, with this test, most of the people that get told they are cancerous are actually healthy people. Well, that seems freaking weird because we'd already decided that this was actually quite a good test. Remember that? This has got only a 2% chance of a false positive and a 10% chance of a false negative, although that part's not so good. But the 2% false positive chance would seem to make you think that most people that are given this positive diagnosis must actually be cancerous. But it's not true simply because healthy people very much are more common than cancerous people. So just by the rarity of the thing we're trying to detect, most of the people that are given the positive diagnosis are actually healthy people that are false positives. Okay, so to continue on with the contingency table theme, I'm just going to show you right here. This is a table from the Wikipedia page on precision and recall. It's going to become your best friend because at its heart, it has the confusion matrix, and it shows you true positives and true negatives, false positives and false negatives on the off diagonal. But it kind of extends that contingency matrix and shows you how to construct the true positive rate by combinations of elements that are here inside the contingency table. Okay, so as you might guess, the positive predictive value is a metric which is composed of true positives over PP, which is the positive predictive value, which is the entire number of positives, right? So this contingency table is built so that you can see each metric at a location where its row and column location tells you how the thing gets constructed, which one of these bits in here constructs it. And we're going to talk in detail during our regular class time about like a third of these. But just in general, different study fields will use all of these things. So anything in color is constructed directly from the stuff of the main contingency table. And anything in white is some sort of like mashed together metric, which is combining lots of different things. Okay, so we will talk more about this in class. Thank you for stopping by. See you soon.